Welcome to chemistry. Our first unit is called The Nature of Science. So what is chemistry? Chemistry is the study of matter. Chemists study the composition, in other words, what matter is made of, the structure, and properties or characteristics of matter. They study the processes that matter undergoes during chemical and physical changes, and they study the interactions between chemical elements. This campfire is an example of a chemical change, which is demonstrated by the heat and light that's produced by the fire. So this is one way that matter can change, and that's something that chemists study. We can use the scientific process and the tools of chemistry to understand the natural world. For example, this Pennsylvania river was contaminated by a nearby coal mine. Chemistry can help us identify what is causing this color in the water and how to fix it. So sometimes we look at things that are visible, and chemistry shows us the invisible world that is causing what we can see. The scientific process or scientific method is a systematic way of analyzing a problem. So it begins with a question, and that question is researched, and that research helps us make a prediction, which we can then test with an experiment, and from that experiment draw conclusions. So a prediction is made based on available research. And a prediction in science we often call a hypothesis. That is a testable prediction. So we're going to test that with an experiment, and a hypothesis has to be a testable prediction. The hypothesis is tested in the experiment, and then conclusions are drawn from the experiment. These conclusions are often shared with the larger scientific community in a process known as peer review. We'll talk more about that in a minute. So let's focus on the experiment part of this process here. What is a controlled experiment? Scientists use controlled experiments. In a controlled experiment, only one variable is changed at a time. The independent variable is whatever is being changed, and the dependent variable is the result of that change. So if, for example, I was testing whether different kinds of music made a plant grow faster, the change, the independent variable, would be the addition of music, or possibly the addition of different kinds of music. And the dependent variable then would be whether or not the plant grows faster or the rate of growth. All other factors in the experiment should remain the same. That's why it's called controlled, and those are called controlled variables. So it's a controlled experiment because only one variable is being changed, and that means that the results are easier to interpret because the scientists don't get confused as to why the results occurred. If we're only changing one variable in the experiment, then if there is a change, it will have to be attributed to that one variable. So if we look at this graph here, this is a hypothetical experiment in which a pharmaceutical company is testing a new antibiotic to treat an illness. One group receives the new antibiotic and one group receives the old antibiotic. So if we look at the graph here, the independent variable is written on the bottom, on the x-axis. So that's the dosage of antibiotic, and we're going to test different dosages here for the new antibiotic and for the old antibiotic. Obviously, if this was a real graph, we would have more labeling on here. And the dependent variable is going to be on the y-axis, And this is going to be the length of symptoms here. So if we change the dosage, how much does that shorten the symptoms for those patients? And we have two lines here because we're testing the change of dosage for old antibiotics and the change of dosage for new antibiotics, and how both of those affect the length of the symptoms. In order to determine if the change in antibiotic is actually the reason that the length of symptoms is shortened, because as you can see here, as we increase the dosage of the new antibiotic, the length of symptoms does get significantly shorter on our hypothetical graph here. In order to attribute that to the antibiotic itself, the pharmaceutical company needs to keep things like the age of the patients, the severity of the symptoms, and the number of doses the same in order to make sure that the change in antibiotics is really the reason that the symptoms are shortened. So again, the dependent variable goes on the y-axis and the independent variable goes on the x-axis. That will be true of any line graph that we do during this course. So in summary, chemistry is the study of matter, the processes it undergoes, and the interactions between it. Like other fields of science, chemistry relies on controlled experiments to collect data about the natural world. So when scientists make measurements in their experiments, they often use the metric system. So let's discover some base metric units. So the global scientific community records measurements using SI units. The International System of Measurement comes from the French name Système International d'Unité, which is SI units, and is commonly known as the metric system. These individuals in the picture are running a 5K, which is short for a 5-kilometer race, and kilometers are a unit in the metric system. There are 5 base SI units that we use regularly in chemistry. The meter measures length. The gram measures mass. Kelvin measures temperature. Seconds measure time. And the mole measures the amount of a substance. This balance measures in grams. It measures the mass of a substance. Moles is something that we will spend a significant amount of time on later in the year. So if a mole doesn't mean anything to you right now, that's okay. How do you convert metric units from one unit to another? Well, here is our chart showing the base unit here, which would be those ones that we just discussed, meter, gram, and so on. And then the prefixes that we put in front of them to show how much smaller or how much larger something is from that base unit. So metric units have prefixes to describe the range of measurements from very small, which would be in our micro area here, to very large. And by using conversion factors, measurements can be changed from one unit to another. So let's discuss conversion factors in a little more detail. First, we're going to, in order to solve a problem converting one metric unit to another, we're going to begin with the number that we have and the unit that's given in the problem. So for example, if we are solving a problem that says convert 14 centimeters to meters, because let's say one published study was discussing measurements from their experiment in meters, and so if you measured in centimeters, we need to be able to compare to that other published study. So if we needed to convert from centimeters to meters, we're We're going to begin in step 1 here with the number and the unit given in the problem. So this is the given number and unit is 14 centimeters. We're going to determine the units desired in the answer, which here is going to be meters. And finding those on our chart here, we have centi here, centimeters, and base unit would be meters here. Multiply your number fact, so our number facts are from here, with what you have at the bottom, the given units at the bottom, and what you want at the top, so the desired units at the top. So if we're starting with 14 centimeters here, we're going to put centimeters on the bottom, and 1 centimeter is equal to 0.01 meters. And so we're going to say 1 centimeter on the bottom, since that's what we already have, our units we already have, and our desired units are meters, so 0.01 meters on the top. And we're going to cancel out those units. So you can pretend that there's a 1 under this 14 centimeters, so we can cancel out, just like in a fraction, you would cancel out units. And then we're going to multiply the numbers across the top and across the bottom. And so that'd be 14 times 0.01 gives us 0.14. And then we have an understood 1 here in our blank, times 1 gives us 1. And then we're going to divide the top by the bottom. 0.14 divided by 1 gives us 0.14. And our remaining units that didn't get canceled out are meters. And that's what we were looking for, so that's the correct answer. What are derived units? Well, derived units are calculated from base SI units. So these are the second tier of units, second tier of measurements that we can make based on other base units. So there are 2 particularly useful derived units in chemistry. Volume. And for the volume of solid objects, we measure length times width times height. And for the volume of liquids or gases, we use a liter, which is calculated by 1 decimeter cubed. So 1 decimeter by 1 decimeter by 1 decimeter of a gas is 1 liter of that gas. Density is also a derived unit, and it's calculated by mass divided by volume of some substance. So the volume of this clock, for example, is 16,380 centimeters cubed, or cubic centimeters, and we got that by taking 45 centimeters of length times 13 centimeters of depth or width times 28 centimeters of height. So in summary, chemistry uses SI units, commonly known as metric units. Base units are standard measurements, but can be adjusted to larger or smaller units by adding a prefix. Metric units can be converted or used to calculate derived units like volume and density. Sometimes scientists make their measurements using scientific notation. Scientific notation allows us to easily express very large or very small numbers. A number written in scientific notation has 2 parts, the coefficient and an exponent. And it will always say the coefficient times 10 to whatever the exponent is. The coefficient must be between 1 and 10. And the exponent tells us how many times the coefficient must be multiplied by 10, sometimes divided by 10. So here's an example. 4.5 times 10 to the 6th is how we read this scientific notation. And this tells us that it's 4.5, that coefficient, times 10 times 10 times 10 times 10 times 10 times 10, which is our times 10 to the 6th. There are 6 tens here. So that number would be 4,500,000. Obviously a very large number, and this allows us to write it a little bit more easily. So if we try some more, you can use your calculator for these. 5.8 times 10 to the 8th is equal to 580 million, or 5, 8 followed by 7 zeros. Working in reverse here, 71,000 in scientific notation. We can do this by moving the decimal back. So if the decimal is here after that number, 71,000 would be 71,000.0. So the decimal point is here. If we move it back to create a 7.1 here, which would be between 1 and 10, 710 is not. So we know we use the 7 and the 1. So we would go 1, 2, 3, 4. We move it back 4 spaces. So that's going to be 7.1 times 10 to the 4th. That'll be the scientific notation for 71,000. If the number is less than 1, it will have a negative exponent. And this situation involves dividing by 10 multiple times instead of multiplying by 10. If there's a negative exponent, it's divided by 10. So here we have our small number, 0.00003, and that would be written as 3 times 10 to the negative 5th. And again, if our decimal point is here, and in order to get a 3 here, we need to have the decimal point here, it would be moved 1, 2, 3, 4, 5 times, and that's how we end up with 3 times 10 to the negative 5th. So practice this one, 8.2 times 10 to the negative 7th. Again, you can use your calculator for these. And this should be your answer here. So we have 6 zeros and then 8, 2. How do we do calculations with numbers in scientific notation? So rather than just having one measurement in scientific notation, how do we combine measurements or combine scientific notation? When adding and subtracting, the numbers must have the same exponent. So this is, again, we're talking about scientific notation numbers here. If the exponents are not the same, you must change a number. So here's an example. If we have the same coefficients and we're adding two scientific notation numbers, we have 3.4 times 10 to the 4th plus 1.7 times 10 to the 4th. Since those exponents are the same, we can just add those numbers, those coefficients together. And we end up with 5.1 times 10 to the 4th. And since this 5.1 is still between 1 and 10, that's an acceptable answer. If there are different coefficients, then one of those numbers will need to be changed. So here's an example, 5.3 times 10 to the 7th plus 4.2 times 10 to the 6th needs to be altered so that these two exponents are the same. And you can alter either of those numbers in order to make them both 10 to the 6th or both 10 to the 7th. I've chosen 10 to the 7th here, so we'll keep the 5.3 times 10 to the 7th the same. And we're going to alter this by moving the decimal one space to the left, because that means that we would need to move it one extra space in order to make it 10 to the 6th. So this number is going to be the same as 4.2 times 10 to the 6th. So these now are equal. Obviously, this is not what we're looking for here, but because it's not between 1 and 10, but it's a temporary fix that allows us to add these two numbers together. So now we can add the coefficients since the exponents are the same, and we end up with 5.72 times 10 to the 7th. So here's one for you to try. Pause the video until you figure it out. And I've decided to convert them both to 10 to the 3rd. You might have chosen to convert them both to 10 to the 1st, but your number should be the same, your answer. So if we convert them both to 10 to the 3rd, we end up with 0.015 times 10 to the 3rd. Again, this is a temporary fix that allows us to have the same exponent. And this one we're going to keep the same. And we add these coefficients together, we end up with 2.515 times 10 to the 3rd. In multiplication and division, the exponents do not need to be the same. So when you're multiplying or dividing two scientific notation numbers, we do not need matching exponents. When multiplying, you're going to multiply the coefficients together and then add the exponents. So here our coefficients are 8.5 and 4.2 if these are our two numbers we're multiplying together. 8.5 times 4.2 is going to give us 35.7, and then we're going to add the exponents here. 3 plus 5 gives us 10 to the 8th, and so the answer is 35.7 times 10 to the 8th, but because this coefficient is not between 1 and 10, we need to adjust it, and so we're going to move that decimal point over to the left, and that's going to increase the exponent by 1. So this will be our final official answer. When dividing, you divide the coefficients and then subtract the exponents. So the opposite process of multiplication here. So we have 6.1 and 7.5. We'll divide those and then subtract the exponents. 4 minus 5 is -1. So here is our temporary answer. Obviously, this is not between 1 and 10, so we're going to change it. We're going to move that decimal point over 1 to the right, and that'll make it 8.133 times 10 to the -2. And I always tell my students to remember LIRD, or LIRD, and that means that when you move the decimal to the left, it increases the exponent. When you move the decimal to the right, it decreases the exponent. So LI, left, increase, RD, right, decrease. So here we moved to the right, and that's going to decrease our exponent because -2 is less than -1. Sometimes we use dimensional analysis as well to convert numbers. And in dimensional analysis, we're converting one set of units to another using relationships between the units. So we might say for every blank, there are blanks. So for this very basic example, maybe we would say for every 1 meter, there are 100 centimeters. So here's an example again. For every 1 inch, there are 2.54 centimeters. So I was using metric conversions here. We can also use metric to English conversions using dimensional analysis. So for every 1 inch, there are 2.54 centimeters. Convert 4 inches to centimeters. So we've learned how to do this already. You're going to start with your given information. 4 inches is given here. And then we include our conversion factor with whatever our given units are on the bottom here. And that allows inches to cancel out. The desired units are going to go on the top. And since there is 1 inch for every 2.54 centimeters, this is going to be our conversion factor. We're going to multiply across the top, multiply across the bottom, and divide these numbers. So 10.16 is what we get when we multiply 4 by 2.54. This is an understood 1 times 1 inch gives us 1 on the bottom. Divide 10.16 by 1 and you end up with 10.16, and we know that our units are centimeters because they're the only ones that haven't been canceled out. Some conversions will take more than one conversion factor. So if this is the case, we generally convert to the base unit first and then convert to a final unit. So if our example here is 0.46 kilograms to micrograms, we're going to stop at the base unit, which is grams, and convert from kilograms to grams and then from grams to micrograms because it's too complicated to remember all the conversion factors from one metric prefix to another. So we start it with our given units, and we use 10 to the third grams for every 1 kilogram. Set it up so that kilograms are on the bottom. cancel out the kilograms, and we are now at grams. We need to get to micrograms, so we're going to add another conversion factor here, and we're going to put grams on the bottom. So it was on the top, now it's on the bottom. That's going to allow us to cancel that out again. And our second conversion factor is there are 10 to the 6th micrograms for every 1 gram. Cancel out those grams, multiply across the top, multiply across the bottom, and divide, and you end up with 4.6 times 10 to the 8th micrograms, which is equal to 0.46 kilograms. This is how using scientific notation comes in handy when we are converting units, because sometimes we're converting from a really large unit to a really small unit. So in summary, large and small numbers can be written easily with scientific notation. If a relationship exists between two units, dimensional analysis can be used to convert between the units. So when we're making measurements in an experiment, how precise do we need to be? Well, it depends on the equipment that's used and the measurements that are available on the equipment. So let's look at two different graduated cylinders here. We have one on the left and one on the right with different increments on them. The precision of the lab equipment determines the accuracy of the measurement, so how close we can get to the exact measurement. So looking at the reading on the left graduated cylinder, what do you think that is? So I'll give you a second to identify what those increments are and then come up with a value that you think is for this, where the arrow is here. You can pause the video until you come up with that answer. So I'm going to say that reading is about 208 milliliters. Yours should be close to that. It's somewhere between 205 and 210, because this is, if this is 250 and this is 200, then these are 5 milliliter increments. So 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 250. What number are we uncertain about, though? That would be the ones place. So we're not exactly sure if that's 208. It could be 207. It could be 206. It could be 209. We're not sure about that ones place. On the right-hand side here, let's take a look at this graduated cylinder. Where is this arrow? What is this measurement where the arrow is? So again, pause the video until you've figured that out. And I'm going to say that's about 39.5 milliliters. Here we are uncertain about the tenths place, though, because we can measure ones very easily here. We've got 30 down here, so this is 31, 32, 33, 34, 35, 36, 37, 38, 39. So it's somewhere between 39 and 40, but we don't know about that tenths place. So it could be 39.4, it could be 39.7. We have some uncertainty there for the tenths place. Significant figures are the accurate numbers that we can identify from the increments provided on our measurement tools, plus one estimated digit. So that would be the unknown part that we discussed on the previous slide. Significant figures are determined by the precision of the measuring device. So we always try to use the most precise measurement tool that we can for the volume or length or whatever that we are measuring. So which of these two rulers is more precise, and what is the estimated digit on that ruler? So the top ruler would be more precise because it has the tenths places marked on here, whereas this ruler does not. It only has half centimeter markings on it. And our estimated digit, since we have known digits here for 0.1, our estimated digit would be the 0.01 place, the hundredths place for that measurement. And what are the significant figure rules? So there are a lot of rules that go along with significant figures and determining how to use these in measurements and calculations throughout our chemistry course. Our first rule is that all non-zero numbers are significant. So none of these are going to be uncertain. These are all going to be significant figures or significant digits that we are going to pay attention to and keep throughout our calculations if possible. So these non-zero numbers would obviously be anything but 0, 2, 3, 4, 8, 9. All sandwiched zeros are also significant. So if a measurement is 206 milliliters, for example, this is going to have 3 significant figures. This 0 in the middle is going to count. We can't just take it out because it's going to give us a completely different number. Trailing zeros are not significant unless they're after a decimal point. So for example, here we've got 1100. That actually only has 2 significant figures. This could be an estimated value, and so we're not going to pay attention to these last 2 digits here because they may be estimated. Because there's no decimal point after that. It's not exactly 1100.00. It's just 1100. So that could be an estimate. We're going to count that as just 2 significant figures. 11.00, however, has 4 significant figures because this shows a level of precision that we would like to keep throughout the calculations so that our answer is as precise as the original measurements that we made. Additional rules here, placeholder zeros are not significant. So these are placeholder zeros here. And if we put a 0 in front of this, it would be 0.0007. Those are all placeholder zeros. It only has 1 significant figure, and that's the 7. And 140,000 also only has 2 significant figures. These, again, we could count them as trailing zeros, but we could count them also as placeholder zeros. They are giving us this 14 in the correct place so that we could have 140,000 instead of just 14. They obviously need to be there, but we're not going to count them as precision numbers. Now, when you're calculating and modifying measurements that are already made, we need to follow some specific rules as well. So when adding and subtracting measurements, you're going to align the decimals and round to the value with the fewest decimal places. So the goal here is that we are trying to be as precise as possible with the calculations. But if you have 1.0 and then for one measurement, and you're adding that to another measurement that is 2.00007 or something like that, that second measurement is significantly more precise. But we can't change that first measurement to be as precise as the second. So we need to reduce our level of precision to whatever the lowest number of significant figures is. So here's our example. We have 2 measurements here, 4.102 centimeters, 3 measurements, 8.4 centimeters and 15.08. We're going to line up those decimal places, and whatever has the fewest number of decimal places is going to be what we're going to keep. So we add all of these up, we get a temporary value here. If we had the same level of precision for all of these measurements that we do for this first one, then we'd be able to use this full measurement, but this value here is not very precise, so we're going to reduce our level of precision to 1 decimal place. So we're going to convert from 3 decimal places to 1 decimal place because this has the fewest decimal places, so it's the least precise. And therefore, this is as precise as we can be with our answer. When multiplying and dividing, the answer matches the measurement with the fewest significant figures. So for example, if this measurement has 5 significant figures, as you can see, no trailing zeros, all non-zero numbers. So these are all 5 significant figures. They're all significant figures. This one only has 2 significant figures. So we're going to divide these out and come out with a temporary value. But because our lowest level of precision here is 2 significant figures, we're going to reduce that to 310 feet per second. Remember, this is a trailing zero that doesn't count. So we do have 2 significant figures here, same as in our original measurement. So here's some practice. How many significant figures are in each of the following numbers? So pause the video here and figure out how many significant figures are in each of those numbers, and then we'll check them. So we'll go one by one. Look at 101 here. How many significant figures does that have? Just as a little quick check. That has 3 significant figures. And 101.5 has 4 significant figures. 0.003, that's 1 significant figure. This 3 is the only one that counts. These are all placeholder zeros. 0.260 has 3 significant figures. This is a placeholder 0, but this is a trailing 0. And so because that trailing 0 is after the decimal point, it does count. 550 only has 2 significant figures. This is a trailing 0 or placeholder 0. And this last one, 70,500, has 3 significant figures. This sandwich 0 counts. These 2 trailing zeros do not. So in summary, significant figures are based on the precision of the lab equipment. When calculating significant figures, the precision is reduced to the measurement with the least number of significant figures. Okay, so all this time we've been talking about measurements and experiments, and now we're going to move on from testing and experimenting to forming conclusions. So how do scientists form conclusions? Well, measurements and other data collected from an experiment can help scientists form conclusions. A conclusion either supports or rejects the hypothesis. So remember, hypothesis is a prediction that can be tested through an experiment. And once that experiment is finished, we draw a conclusion, and that conclusion can either support or reject that hypothesis. Is the conclusion proof that our hypothesis is true or false? No, definitely not. Science is not used to prove that something is true. So just because you do an experiment one time does not prove that it's going to happen like that all the time. We can disprove something by doing an experiment that shows that a hypothesis is wrong, or we can be fairly certain that our hypothesis is correct because we've done the same experiment numerous times. But there's always a chance that one time it could give different results, and so we don't ever use experiments and conclusions in scientific processes to prove that a hypothesis is true. By repeating the experiment, scientists can be more confident of their results. And they also share data with others, and that helps the whole scientific community to further our knowledge. So that one scientist doesn't need to be doing the same experiment over and over. They can combine results with other scientists to determine if they've got the same or similar results. And that lends more credibility than one scientist doing all of the experiments because their process could be flawed or their interpretation of the results could be biased. So what is peer review? Well, when an experiment is complete, the scientist often submits the results of the experiment for peer review. And peers are individuals at the same level of education or specialization as whoever is the scientist running the experiment. You also, of course, have peers that are at the same level of education as you in your high school. Those would be your peers. If the peer reviewers are satisfied, the experimental results may be published in a scientific journal. So I think it's important to remember here that scientists that are running a peer review usually have very advanced degrees, and so they are well qualified to analyze the results of an experiment and see if there's any flaws in the process. So when you're looking at scientific journals for research, looking at peer-reviewed scientific journals will give you the most accurate data and the least amount of bias and opinion in the conclusions because it's been looked at from several different scientists. Peer review is one of the most important ways that the scientific community guards against faulty science. So we said that a scientific conclusion does not prove that a hypothesis is correct. And so we have some terminology that relates to that in the form of theories and laws. And scientific theories and laws are a little bit different from each other. And scientists do not use the term theory in the same way that non-scientists do. So you might say, I have a theory that someone's stealing packages off my porch. That's more of a hypothesis. Scientists do not use that in the same way. So they do not use the word theory in the same way. So scientific theory is a comprehensive explanation based upon evidence that predicts a feature of nature. So the evidence is from results of past experiments. And we generally say that a scientific theory predicts how or why something is happening. A scientific law, on the other hand, refers to the rules for how nature will behave under certain conditions. For example, the law of gravity explains how an object will fall when it's released from a specific height. So a law generally explains what is happening, and a theory explains why or how that is occurring. So if we were to compare these two, a theory is explaining why a natural phenomenon occurs. A law is explaining what is occurring. And they are both based on a hypothesis and supported by evidence. They both involve making predictions, and they both can be revised. These can be very easily revised if the evidence or experiments start to show something other than what we had already seen. In summary, by repeating experiments and submitting results for peer review, scientists can be more confident about their conclusions. This can lead to scientific theories, which provide evidence for why phenomena occur in the natural world.